All right, good afternoon, everyone. So today, well, I guess by now you all would have gotten the first tutorial. And would have heard about the changes we have. So we got final confirmation from the university last week about the courses and so on. So this is it that we're doing now, that we will have um, the 5 assignments being the um, the 4 labs, and the labs have the usual labs plus some theory questions at the end, and then you'd also have that one project at the end of the course, towards the end of the course, which would be due not during the semester itself, the teaching part of the semester. It would be due towards the end of the exam period. So you have some more time to work on it. So this is the provision that the university has made for 100% coursework courses, because you don't have an exam for the course. So you could use the time that you usually take to study for the course for the exam. You could use that time to do your coursework for that course. So you don't lose time like that, right? So today what we're going to cover is the tutorial, the Transformers tutorial that we had online. I trust by now everybody has done it. You'll see the tutorial here. And what we're going to do is all the theory questions and so on, those things are straight out of notes. So I'm not going to bother too much about those. We're going to look at the calculation questions. So let us start. I assume everybody has this tutorial up. So I'm going to move it out of the screen so that I can write on the whiteboard and or show you the MATLAB and so on as necessary. So, well, actually MATLAB has a question on it, so maybe I could just use that. Right. So for question 6, the question says, a single phase transformer, 180 turns on the secondary side, and please remember to mute yourself unless you have a question to ask.
What's that? Mommy, let me see people's phone.
So, so the transformer has 180 turns and 90 turns on the secondary and primary. So the secondary is 180, NS 180, NP 90, and the resistance is, again on the secondary and primary, 0.233 secondary resistance and 0.067 for the primary resistance. Now notice here that we'll have the secondary has more turns, the primary has less turns. So it means the secondary has a higher voltage than the primary and a lower current, and the primary has a lower voltage and a higher current. So notice that the resistances here, the lower current side has a higher resistance and the higher current side has lower resistance. And that makes sense if you think about it, because if you have a higher current winding that has to have a higher current, it's going to be a thicker winding. When you look at the transformer windings, you'll actually see, this is one of the ways you could tell which is the high current side and which is the low current side, is the windings would be different sizes, because a thicker winding, just like for your house winding, your house wiring, you'd know that when you did that project last year, if the circuit is rated for more current, you have to use a thicker conductor, right? So a thicker conductor means a conductor with a greater cross-sectional area, and therefore you would get a lower resistance, because the resistance is rho L on A. So as A goes up, the resistance comes down, right? So, so here we have now to calculate the secondary equivalent resistance when referred to the primary side. So this is just referring parameters, and we know the resistances, they scale with the square of the turns ratio. So we're going secondary to primary. So this NP on NS squared multiplied by RS, that one, which gives us 0.0583. RP is NS on NP squared multiplied by RP, and that gives us 0.2680. And R equivalent primary, and this is what you'd have to do a lot of times for the questions you're doing. You want to bring everything to one side and come up with one combined impedance. In this case, we're just looking at the resistance. So we have the primary side, which is not the referred one, the original primary side resistance. And then we add it to the equivalent of the secondary, which is if we take the secondary resistance and we refer it to the primary side. Good? Everybody following so far? Yes? You could write in the chat, or you could just use your what you call those things? Reactions. Good. Nice. So that is it. That was a very simple question. So, okay, so somebody wants to go it over again. So let's look at it on the diagram, on a diagram. So we have here the ideal transformer, right? We have 180 turns, sorry, on the secondary is 180 turns. And we have 90 on this side. And the question says that on the secondary side, we have this resistance, which is 0.233. And on the primary side, we have this resistance, which is 0.067. And the question is asking us to refer the parameters. So we're going to take our, first we want to find what is the secondary resistance when referred to the primary side. So to do that, we have to multiply by the square of the turns ratio to the side it is going on. So since it is going to this side, this is NP and this is NS. So I have to multiply by the square of NP on NS, right? So you'll see here, that's exactly what we did. NP on NS squared multiplied by RS. And that gives us the equivalent resistance of the secondary when looked at through the primary, right? And that is important because when you measure, you often measure on one side. So you measure the primary side, and when you measure the primary side, what you are actually measuring is the primary plus the secondary. So if you measure on any side, you're going to measure the effect of both sides. So you have to know how to disaggregate them, right? So that is why this reflection referring the parameters is important. And then we do the same thing for the secondary. For the primary, we want to go from this side to this side. So we multiply, so here we multiply by NP on NS squared. Here we're going to the secondary side, so we're going to multiply by NS on NP squared, right? Multiplied by the primary resistance. So that is it. And then the last part asks you the total equivalent resistance when referred to the primary side. That means that essentially we're going to have RP and then RS equivalent, right? Usually the diagram, we will note this with RS prime, right? That is typically the notation we would use. Of course, you can't write this in MATLAB, so that is why I use the EQ to mean that it is equivalent, right? And then, of course, when you refer the parameters, the other side will become short-circuited when all the parameters are referred. So, and why does that happen? So if you look here, let's say the thing was originally open circuit, right? So we have right? Or we have some load in it. Then every time you take this and put it on this side, what you're doing is you're short circuiting this component. Right? So the voltage that appears over here now appears over here, or well, when you refer it on this side here, right? So here, I actually should have had put in a load here for that, if we wanted to do that. So that is why you'll see in the next question, you'll see that come up when we have a load in this position and you move it to the other side, you will see that we end up with a dead short on this side, because we would have referred the parameters, then we would have referred the load, so we would end up with a short circuit, right? So let's go to that question now, and we will see how that actually comes into it. So the next question right. So number 7, the diagram below shows the equivalent circuit for a single phase transformer with resistances and reactances given in ohms with reference to the primary side of the transformer. So 0.16 and 0.7 ohms here. And the ratio of secondary to primary is 10. So NS on NP is 10. Load impedance is 5.96 plus J4.44. This, of course, is not W. That was an ohm symbol that got converted to plain text, referred to the primary, right? So it says that when it is referred to the primary, it is this value. Here, the load is being shown on the secondary, right? And then we are asked to calculate these things. So what we have here is let's go back to this diagram. So we have the circuit. And there was some load here. Good. And the equivalent resistance, so this is R1, RP plus RS prime, and this is J omega LP plus LS prime. Or you could say XP plus XS prime, right? J XP plus XS prime. Either way you want to state it is fine. And now we have this load here, Z load. But we are not given what it is here. We're given what it is at the other side, right, when it is referred to the primary. So what we are actually given is this coming to this side, which would be and then we have our leakage parameters, and then we have our load. So the question is now, what is on the other side here? So when we refer the parameters, we replace what is on the side that we referred it from with a short circuit, right? So for example, up here, when we got RS coming to this side, we had a short circuit here. I should actually leave this part open here. So it was originally like this. And when we carry it on this side, it short circuits this here, right? So now what we have is the load from the secondary. When it goes to that side, we're going to get a short circuit here. So that the voltage across here is actually 0 volts, which means the voltage across here is 0 volts. So the voltage that we would have seen across this load here now, that represents the load voltage, is actually going to show up here. So this is representative of the load voltage, right? And that is the key really to this question. So we want to calculate what is the primary current and the secondary terminal voltage and efficiency of the transformer, right? So the primary current will be the current here, which is a sum of this current plus the no load current, which is a sum of these two, right? Let me draw this part here better, so it will be a little bit easier to look at. So it is a sum of this current, which is the no load current, right, plus I1. So we could get now, we know what the voltage is across the terminals here, which is 200 volts, V in. And we know what these values are here, 400 and J231. So I can easily calculate what is the current in each one of these branches. Then I know what these values are, 0.16, J 0.7, and this one is 5.96 plus J 4.44. So I know what these are. So I could calculate the current here with V over R. I could calculate the current here with V over X. And I could calculate the current through here. And this is the important part. This is why it is important to know that this was short-circuited here, giving us 0 volts on this side and 0 volts on this side. If we didn't know that, if this was open-circuited here, we wouldn't know what the voltage is, right? So if this was open-circuited here, I couldn't tell what the voltages would be. So I would not know, because it is being energized from this side, I would not know what the voltage is going to be on that side. Like if I had some unknown resistance, I could say tentatively, if it was open circuit actually, if it was open circuit, I could say, well, no current is flowing through here, so no current is flowing through here, so the voltage would be the same across here. But then I would get 0 volts over the load, right? So if I left here as open circuit, when I did this, when I took this to the primary side, if I left here open circuit, I would get IS is equal to 0. That would make here, or let me say I2 is equal to 0. That would make I1 is equal to 0. That would mean that the voltage here is the same as the voltage here. So I get V in here, V in here, so that the voltage across this whole thing is 0. Right? So it would give me that it would tell me that the voltage across the load is actually 0. But we know that is not true. If I had the load on the secondary, the voltage across the load would not be 0. So the proper way to do it is every time you refer the parameter to short circuit it. And that would tell me now that this is 0 volts and this is 0 volts. And now I could get the current running through this load, I1, to be equal to the 200 volts over the sum of these impedances, 0.16 plus 5.96 plus J 0.7 plus 4.44. And that would give me my current. And once I have that current, I could multiply that by the impedance here to get the voltage drop over the load. Or I could just take it as a voltage divider. I know the voltage here is 200 volts. Right? I know the I know the voltage here is 200 volts. I know the voltage here is 0 volts. And I have some impedances between them. So I could use my voltage divider and get what the voltage across that is. So let us look now and see in MATLAB what it looks like. So we have 200 volts. The Z equivalent is 0.16 plus J 0.7 R0400 XM231J. Remember in MATLAB, if you want to just write the imaginary number, the J has to come after it, not before. If you want to put the J before it, you'll have to put a multiplication sign. Like you'll have to do it like this, J multiplied by 0.7, right? Z load primary is 5.96 plus J 4.44, NS10, NP1. So first thing we're going to do, the first thing we wanted to get was the primary current. So we're going to calculate all the different branches. I0, which is the current through the no load branch, the resistor, the core loss, Vn on R0, Im, Vn on Xm, and the I no load will be just the sum of these two in that parallel branch, in those two parallel branches. And then we want the primary current, which is, well, this here, we usually have it as I1, right? So let me see if we could, let me put it as I1 here just for clarity. I1. And I do not find and replace all in case there's any others, right? So, right, so I1 is V in over Z equivalent plus Z load referred to the primary, right? Which was this entire thing here. Good? Which one of them is these things? No, that's not it. Oh, look, I have it here. Right, good. So we find I1. We find I1, and you'll see here, I just put the magnitude and angle. And then we want to get the input, that is will be the sum of these two, the no load plus that I1 current. And then if I want to get the voltage across the load, this Vs, which is the secondary voltage, referred to the primary, then it is I1 multiplied by Z load P. So that gives me some particular voltage. And this is that voltage here. And then when I want to find out what the voltage is actually on the secondary side, I multiply by the turns ratio. And that gives me the answer here. And then we can look at the absolute value and the angle and so on of the voltage, if you want to put it in phasor form, right? The next part of the question asks, what is the second? Oh, so we did the first two parts of the questions. The last part is the efficiency of the transformer. So efficiency, of course, is P out and P in. This is just converts from radians to degrees, right? So when you use this function in MATLAB angle, it returns it in radians. So this just converts it to degrees, since we are accustomed to seeing it in degrees. You could also multiply by 180 and divide by pi, right? So if you multiply by 180 divided by pi, you'll get the same thing. So IS is, right, so we're off to the efficiency. So efficiency is P out on P in, or you could do P out over P out plus losses, or P in minus losses over P in. All of those will give you the same thing. So here we have P out, which is I1, which is the current going through the load on the primary side, multiply, so I1 squared, and notice this is the absolute value. Every time we find power, we have to get what is the value of the power. We have to use the absolute value of the current. We have to use the magnitude of the current, not the complex value, right? Or not the real value, or not the complex value. We have to use the absolute value. And this is very important for what you'll be doing in MATLAB and the answers you'll be submitting, because anytime you use power, you have to make sure that you're using this absolute value, right? So I squared multiplied by R, which is the real part of Z load, right? So there's one question whether we have to scale Z load primary as well. No, we don't have to scale it because we're using the current I1, which is on the primary side. So if we use the secondary side current, then we would have to scale it. Remember, the whole basis of converting from primary to secondary is actually preserving the power. So if you find the power with it referred to one side, it would be identical to the power referred to it on the other side. So here, since you already have the impedance on the primary side, we already have the R on the primary side, and we already have the I on the primary side. We don't need to take it back to the secondary side to find it. It would be identical, right? So we have here now I1 squared by the real part of Z load. And now we are looking at the real part, which is just the resistance. So this is one of the important things to remember. The current that we're using, we have to use the absolute value, which is the magnitude of the current. But for the impedance, we use the real part. We don't use the magnitude of the impedance. We use the real part. It is only the resistance that matters for power calculations, right? Everybody good with that? So that's a real important thing. Pay attention to it. Make a note of it if you have to, because these are the sorts of things that cause people to lose marks. They can't remember, they just remember something about his absolute value, and then they just put absolute value for both of them. Or they remember his real value, and then they put real value for both of them. So absolute value for the current, the magnitude of the current, phase doesn't matter, right? For the impedance, it is the real part that matters for power, right? Not the absolute value. All the inductance and so on doesn't matter. That's the power in the inductors just circulate in the system. It is the real power that represents the power being used to do work and the power being dissipated as heat. And then we have the input power. So we take V in, right? And here, just to be consistent, let me put it as absolute value of V in. It wouldn't make a difference for the calculation because the V in had an angle of 0, but just to be consistent, so that with the formula, which is modulus of V in and modulus of I in, right? VI cosine theta. Remember, if we write P is equal to VI cosine theta, we write it like this. So that in MATLAB code is absolute value of V multiplied by absolute value of I, right? That is what these two things here are. So just so we don't have that confusion, right? So we put in the absolute values. of V in, absolute value of I in, and then we could even say, let me put it in here, angle V in minus angle I in. Again, the angle here was 0, so it doesn't matter, right? But just to be clear, just for clarity, I'll put it in here. And so we have P out and P in, and then we could find the efficiency, P out over P in multiplied by 100, right? Everybody okay there? Yes, yes, yes. No, no, no. Good. All right. Last chance for anybody to ask questions on this one before we move forward. Somebody must have a question. If you feel ashamed to ask a question, ask it anyway. Yes, abs means absolute value. So that just gives you the magnitude. So say we have a, complex number A, which is equal to 3 plus 4j. Then if I take abs A, I get the absolute value. And if I take angle A, I get the angle in radians. So if I want to convert that, I can multiply by 180, divide by pi, and that will give me the angle in radians. In degrees, right? So some important stuff here for you to note for MATLAB, but I expect that a lot of you would have used those functions before. Good. So now on to number 9. So we have a single phase oil-filled 150 kVA, 230 to 6600 volt power transformer with an equivalent series impedance referred to the high voltage side, which is the secondary side this time, of, this should be ohms again because of the font. So 5.34 plus J7, 16.76 ohms. No load losses are 700 watts. Transformers operating under full load at 0.8 power factor lag, energized on the low voltage side. So now we want to find the voltage on the output of the transformer, the regulation, the load current, and the load current required for maximum efficiency and the maximum efficiency of the transformer. So first we declare all our variables. So 150 kVA, 230 volts on the primary, 6600 on the secondary. You'll see here I put in these R's. These R's were for rated, right? Of course, when you get your question, so let me see. So if somebody has a question here. If you refer to secondary with the same NS or scale, if you refer to the secondary for, yes, so if you refer to the secondary, the same thing would apply. You would have to convert all the things, even if it is for the core branch, it will apply on that side as well. And that is because the voltage is going to change. The voltage across it is going to change, right? So when you check V squared on R, that should remain the same. So, right. So P no load. So again here, these are the rated values, right? That's what the R's here for. In your assignments, in your module assessments, we will tell you exactly what these variables should be named, right? And these things, a lot of the calculation questions are being auto-graded. So if you don't use the correct values, as I told you before, if you don't use the correct things, it's going to throw up an error. And I will upload between today and tomorrow the checker for it, right? So you can check your syntax, but I showed you how to check the syntax already. So even if you want to do it ahead of time, you could check it just by declaring the variables first in MATLAB, then pasting your code underneath and see if it throws an error or not, right? So P no load, 700 watts, power factor 0.8. Let me just make a note here, lag, right? So we want to get the voltage output on the transformer. So the primary side voltage is equal to the rated voltage. And we want to then get, so what is the information we have? We have everything referred to the secondary side, right? So if we look at the circuit diagram now, we have everything referred to the secondary, right? So we have the equivalent here. So we have Z equivalent and we have Z load. And then we energize here with the rated primary voltage. VP is equal to V primary rated, right? So that is what we do. Good. So I in, the magnitude of I in is S on V. Remember, S is equal to VI conjugate, right? So the magnitude of S, if we just take the magnitude of that, the magnitude of S is equal to the magnitude of V by the magnitude of I. So here we're just calculating the magnitude of this, and then we're calculating the angle. So this is that is just to show you, this is our cos of that in degrees, which will give you 36.8699 degrees, right? So if we want to find out what is the input current is I in magnitude multiplied by cosine theta minus j sine theta, right? So actually I should take off this here. Otherwise I'm going to get an error, right? Because this calculates in radians. So you'll see something slightly different there. So theta is, so I can calculate the complex value of the current, right? And I calculated that complex value of the current because I knew what the power was. So I knew S was equal to, I can't remember what it is off the top of my head, whatever it was, and I knew the power factor. I know the voltage here, so I could calculate the current coming in, right? So S is equal to VI conjugate, right? So I is equal to, or magnitude of I is equal to S on V. So that is essentially what we did. And then to get the angle, we put in the angle of the power. Or if you want to look at it another way, we could say I conjugate is equal to S on V, right? But we only had the magnitude here. This is cosine inverse 0.8. Right, so that is how we get the angle for the current if we leave it in vector form. Right, good. And you'll see here I made a note that we're using negative, and that is because it is the conjugate value, so we have to take care of that conjugate sign. If I just left it as positive, I would get I would be computing S is equal to, I would be computing it without this conjugate, right? If I just divide it, it would be without the conjugate. If I use the positive value, so if I did I cosine theta plus j sine theta, then this would be this equation here without this conjugate. So remember, all the conjugate is if you have a complex number here, the conjugate is here with the negative of the imaginary part. So if I calculate I based on this, the conjugate is just taking this and making it the negative, which switches the angle from here to here. Everybody okay with that? Yes? All right. Good. And I'm going to upload this, this for you so you could check it out after. I assume everybody has done it already. So, so now, right. So now we have I secondary. And to get I secondary, again, we use the turns ratio. And the turns ratio here is given by the rated primary and secondary voltages. Since you're using current, it is primary over secondary to go to the secondary, which is the opposite of what happens with the, or the inverse of what happens with the voltage and the impedances. And then to get my secondary terminal voltage, essentially what I'm doing here, right? You'll see V secondary rated minus IS multiplied by ZEQ. So what I'm doing is I found this current, I multiplied by the turns ratio, got this one, right? There's no resistance, no impedance here. So this voltage here will be VPR, which means here will be VSR, the rated value. And then all I'm doing is I'm subtracting this voltage here to give me this one here, right? Because this is the V terminal that I want. So you'll see that here, the rated voltage on the secondary, right? Let me see if I can bring this up side by side. So we have, I'll just redraw it. Right, so we put in V primary rated here, and since there's no impedance, we get V primary rated here, which gives us V secondary rated here. We calculated I primary based on our current or power and the power factor, right? And then we used our turns ratio to give us I secondary, and these are the complex values that we have, right? So we found the complex value there. And now I want to get this one, V S, right? So I have to take this voltage and subtract it from this. So that is this equation here, VSR here minus I secondary multiplied by ZEQ secondary, which is that. And that gives me this result here. Right? So that is how I calculate the secondary voltage. Then the regulation is the absolute value of the, it is basically the open circuit voltage minus the full load voltage on the secondary over the full load voltage on the secondary. So we have, for here, it would be V no load minus V full load on V full load. And some places you will see this given as V no load, right? That is an alternative way to do it. We adopt the full load convention. If the transformer is good, it's not going to make that much of a difference. The value is supposed to be close in any case. So you'll notice with transformers that you get some discrepancies. If you look at the standards and so on, usually the way you think about a device, like when we come to motors, you'll notice that when a motor is spec'd, the power requirements and so on, the horsepower that you are given would be on the output, because you want to know when you buy the machine, you don't care about all the losses and all of that. All you want to know is whether this could move your load. So if you know the load, you want the motor spec, the value on the motor spec to be the value that it could move. So you could just say, yes, this meets my requirements and I could get it. But that's because the motor is a sort of end-use device. But the transformer is really a through device. So the transformer is really, well, the power is in is equal to the power out, and you're just transforming the voltage and current. So power, you'll see that there is one power factor or one apparent power rated for the transformer. And traditionally, they would say, well, if you take that power and you use the primary voltage, you get the primary rated current. And if you take that same power and you divide it by the secondary voltage, you get the secondary rated current, right? But that itself is a big approximation because the core loss is there. So if I take, say, my secondary of the transformer and I calculate a current there, right? And then I transform it to the primary side, I would get the primary rated current. But then there is this core loss in there, which is also taking some current, which means the current that comes from the terminal is actually more than the rated current. So, so it is not, it doesn't make sense mathematically. It is not extremely consistent with theory. What you see in practice, and standards for transformers have been changing over the time. So even now, what you'd see there are ANSI standards, IEC standards, and they all define things in slightly different ways. But it was all because the transformer originally, the way it was defined, it missed that piece of information. But in practical terms, it didn't really make a difference. It wasn't going to throw off anything by that much. It wasn't going to overload your transformer to such an extent that it was going to cause any big difference. So the rating there was really an approximation for a quick check as to what is happening. And it was a very good approximation. But if you try to work out things, if you try to work it out critically, if you try to put in all the details and see how things add up, it wouldn't add up, right? So typically, that's why for the questions you would get, we will define like the power factors on the input side, right? Whereas usually it would make more sense if you take a device to define power on the output side. But we define it for the input side so that when you do your calculations, you don't exceed the secondary voltages, right? As you will see if you do some of the questions. I think there was actually a past paper question with that, where we took it on the secondary side, and when you calculated the voltages on the primary side, it was actually more than the rated voltage. And then the question was, well, what is wrong here? Right? So anyway, that is just to tell you that none of like these things like regulations and so on, there's no absolute right or wrong in it. When you look at whether it is full load or no load or so, a lot of them, they just give you some information about the transformer, and whichever one you adopt, you just have to make these little adjustments to the values that you'd get, right, in telling you how good the transformer is. So this value on top would remain the same. The full load voltage, of course, would be lower. So if you use full load voltage, your regulation would be worse because you're dividing by a smaller number. So you're going to get a bigger percentage regulation, which means a bigger fluctuation in how much the load voltage drops for the load. And for transformers is how that is the main mechanism through which the utility will regulate the voltages on the system. So usually the output voltage is the important thing. Like you want TNTech, you don't care what voltage TNTech generates. What you care about is what voltage you get home. And the way you get the voltage home to be within particular limits, or at any industry or so, the way you get that to be within a particular limit to be at the voltage you need is by TNTech adjusting taps on the transformers. The transformer taps effectively change the turns ratio of the transformer. So the more you load the transformer, the more you're going to get voltage drops here, voltage drops on your lines and so on. So what you do to get the voltages in the system to stay within limits is that you would change the taps on the transformer. So you'd increase the turns ratio a little bit or decrease the turns ratio a little bit so that you could change what the output voltage is, right? So we're not going into tap changing transformers and so on, but basically that is all it is. You're changing you're changing the turns ratio of the transformer. Good. Right. So we have the regulation here that we calculate at 5%, 0.51, 0.0512. And the last thing we have to do is we have to find the efficiency, or we have to find the load current for maximum efficiency. So we have to get first the secondary current for maximum efficiency is 700, which is the load power, divide by that load, the resistance, right? That resistance is the equivalent resistance of the high voltage side. We are equating it to the losses in the no load branch, and this is what gives you the the maximum efficiency occurs when these two losses are the same, right? If you go back to your notes, you'll see how that is. What is the calculation for it? Essentially, you have to do the same thing that you'd have done in circuits, which is you just form your equation for maximum power transfer for the maximum efficiency, and then you look at the turning point of it, right? By differentiating and so on. And you'll find that that is the condition. So we just equate what we get, what is the current, what is the magnitude of the secondary current that would give us this, this power of 700 watts. And we find from that the percentage of the full load current that we would get, right? So then let me see what is the next part of this question. Right, so we found there the current for maximum efficiency over the full load current. So that gave us the percentage of full load current required for maximum efficiency. Next, we have to find the actual maximum efficiency of the transformer. So we want to use now this new current that we calculated to do our calculation. So we know what the losses are because we have 700 watts for the series losses and 700 watts for the core losses. So that's 1400 watts. Or if you want, you could actually go and calculate the losses, the copper losses, and so on for it, and by using the actual values of the voltage and current. So all we need to find now is the input power. So the input power, we are going to get, we have to refer this current to the primary, and we are assuming that the power factor is the same. So we refer the magnitude to the primary. So we multiply by the turns ratio. Again, since we're going secondary to primary, since we're going towards the primary side, the primary is on the denominator. And then we want to find input power. So we have V, the magnitude of V, multiplied by the magnitude of I, multiplied by the power factor. And then you could just do P in over P out, which is P in minus losses on P in. And actually this, I think I have the wrong thing here. Do I? P in, where did I get P in from? P no load 1700. This could actually, I could just turn this into 1400 watts here, right? And you'll see it remains the same. So I had it somewhere. Oh, PCU's T no load. Good. So, so you could use it, you could take it as 1400, which would be the same thing as this PCU and PNL, setting it to 700 watts each, right? And then you have PN minus P no load, sorry, PN minus P losses over PN, and you get the efficiency at 97.68. And if we calculated the full load efficiency from before, with the currents we had before, you'll see it is 97.12. So not a huge difference in the efficiency there. Although even small changes in efficiency, like just 1% or like 0.5% change in efficiency, could translate for the utility into millions of dollars, right? So often when we do power systems optimization, and for example, that we have some work going on with TNTech now, where we're looking at optimizing their system, is very small changes in optimization, very small changes in parameters, and you see like hundreds of thousands of US dollars per week in changes in the cost of fuel that they would have. So anyway, that's beside the point. So that is the end of question 9, and we're going on now to question 10, where we have a single phase. Just by the way, when we have it side by side like this, are you all okay with that, or is it too small or so on your screens or anything, or is it fine? I don't want to go forward. It's good. Everybody else is okay with it? All right, great. So single phase transformer, 120 kVA, 66 to 230, 60 hertz pole mounted distribution transformer. That doesn't really make a difference to the question. Equivalent series impedance 2 plus 9 J ohms. Again, refer to the high voltage side. No load losses are 200 watts. So again, we have this same sort of scenario where we have that's not the one I want. Right. So we have again a transformer 230 or 6600 to 230 volts. And here it is referred to the high voltage side. So we have everything on the primary side now, which is the 6600 volt side. So you have to make sure and read your question carefully so that you don't just automatically assume that the high voltage side is the secondary, right? So we have the impedance here of 2 plus J9, and then we have the secondary here. And we have the turns ratio 230 to 6600, right? Remember this voltage, you will only see if it is open circuited. You're not going to see these voltages. You're not going to calculate these voltages on these points here, E1 and E2, unless it is open circuited, and then you have the rated voltages. So we only use these rated voltages really to calculate the turns ratio. When we put them here, that is equivalent to N1 and N2, right? So we want to find the output voltage on the secondary when it is delivering rated load at 0.75 power factor lag, and the input is maintained at 6600 volts. And again, we're going to look at all of that on the primary side. So we declare our variables. We have S120 kVA, VHV, V high voltage, rated 6600, V low voltage, rated 230, Z equivalent on the high voltage side, 2 plus 9J, right? And the no load losses, 200 watts. Good. So we energize this with 6600 volts. We want to find what the input current is. So that is S on VP, and we get that with an angle of theta. So I calculate the magnitude, which is S on VP, because the S I was given with this 120 kVA, right? That is just the magnitude of S. The angle of S is actually given by the power factor, right? Remember, the power factor angle is the angle PQS. So this is this angle theta here, which is the power factor angle, which is also the angle. This S is equal to VI conjugate. So if V has an angle of 0, then I and S have the same angle, just one, the I is the negative of the S, right? So this one, because it is a lagging power factor, S has a positive angle, I will have a negative angle. So that is why we put in here now, again, the negative sign in calculating the complex value of the current. So we will have, again, this was just like the one before, we have to take care of the conjugate sign, and that is how we take care of it, right? So that works out an angle of minus 41 degrees, or the complex value here. When you are working out your questions, you don't have to go and do afterwards put in these things unless you're explicitly asked for it. This equation would be all you would need really, because the software will check what the answer is and will automatically, once you have the A plus JB correct, then the magnitude and angle is already built into that. So I just put them in here so you see what the magnitude and angle would be, right? So we calculate this I in. Then we have V secondary is equal to VP minus I in by Z equivalent on the high voltage side. So here, so this is V secondary referred to the primary side. So that is just calculating the voltage drop across here and getting this value here, right? So that is the voltage on referred to the primary side, and then to get what it is referred to the secondary side, I just take it over with the turns ratio. So the question now is, well, what happened to the primary branch, right? Because usually, if I calculate that, there is this primary branch here with a resistance and an inductance. So what happened to that? Because the value of current that I calculate here is actually different to the value of current that is here. This is I in and this is I1. What happened to it? Well, I just ignored it. That's what happened to it, right? And this is just to show you that these things, when you come to transformers and you're working at full load, the effect of this is negligible. So these are all good approximations. So that is purposefully there in this question for that, right? So we just ignored it. There's no big difference in it. When you get your questions for the exam, do not ignore it, right? You can't ignore it. There's actually not enough information in this question to get this value properly, because we don't have the value of this inductance. But the questions you have for your tutorials and so on, they do not assume that you have to ignore anything, right? This is just put in here so you get an idea of the way people do things practically, right? Like what are the practical things that people do that still give you good results, right? So right. So that was the secondary voltage that we have here, the terminal voltage. Now, that's how we call the terminal voltage, by ignoring the current coming through this branch here, right? So, and of course, you'll have your load connected here on the secondary. So now we want to find what is the efficiency. I don't think this is applicable here, right? So we want to find what is the efficiency of the transformer, efficiency and regulation, finding efficiency and regulation. So the copper losses is the absolute value of I squared by 2. 2 would be the real part here. Actually, let's put that in here. Real part of Z equivalent high voltage. I believe that is what we had here, Z equivalent high voltage. Yes, right? So real part of Z equivalent high voltage, right? You'll see that it doesn't change at all. It's the same value. So that is how I get the copper losses. That is the losses here, right? In this series branch. The other loss is this one here, which I was given as 200, I believe it was, P no load 200. So the total loss is this copper loss plus the no load loss. And if I want to find the input power, it is simply S multiplied by the power factor, right? So I can find it in multiple ways. Remember, P is equal to S by the power factor, which is the same as S cosine theta, right? Which is the same as P is equal to VI. Remember, VI is S, the magnitude of S, multiplied by cosine theta. So all those things could work, right? You have V, you have I, which you calculated, I in with its magnitude and angle. So the cosine of that would go in here, but there is no need to do any of that really, because you have S and you have the power factor. So that is the simplest way to get it. All of them would give you the same thing. They're just because they're all from the same equation. So I calculated P in as S multiplied by the power factor. The efficiency is P in minus the losses over P in, right? And that gives me my efficiency of 99%. And the regulation is again the no load minus the full load over the full load. So here I have VL, V low voltage rated minus the absolute value of VS over the absolute value of VS, right? Which is the secondary voltage at full load. So that is it. Any questions? So what I want you all to realize is that transformers and all the things we're going to do here is really just circuit analysis, right? It's the same circuit analysis that you did in ECNG 1000, exactly the same things. It is actually simpler because we have set topologies. So you're not going to get these random circuits with 10 or 12 nodes and just random things connected to it to work it out. All transformers look the same way. The equivalent circuits look the same way. All DC machines, the DC machines have 2 or 3 variations, but they're very simple. They're all these simple circuits with 4 or 5 components in them, max, right? DC machines are simple. They have just a voltage and 1 or 2 resistors. Same thing for synchronous machines. The synchronous machine is just a voltage source with an inductor in series with it. The induction machine is almost identical to the transformer. And actually an induction machine, when we look at the construction, you'll see the induction machine basically is a transformer that you could move the secondary. The secondary could rotate, right? And that's basically what an induction machine is. So when we look at the equivalent circuit of the induction machine, you'll see is basically identical to the transformer equivalent circuit, right? So the thing that you have to make sure you get all these things like the absolute values, when to use absolute value, when to use the real values, and so on. The AC analysis, that will be the thing that will most of the time trip you up. But once you get to grips with that, you will be able to easily work out all the questions, because all it's asking you to do is calculate voltages, currents, and power, right? You draw your circuit diagram, you could see which current is required, you could find the currents, you could add them up, you could find your power, and so on. So it's not difficult, but it requires practice to make sure you don't make some of these errors. Good? Any questions? Okay, well, that's it.